Okay, so this is the first of a series of short videos about probability bounds, which is Pishro-Nix Chapter 6, Section 2. So the use of probability bounds is that sometimes you do want to estimate probabilities. As he says here, sometimes you need to guarantee the reliability of a communication system or some other system, and you want to ensure tolerance or error tolerance. So as long as you can get the error below a certain value, that can be sufficient for your design. So there are ways of doing this without explicit calculation that are based on statistics like the mean and the variance. If I know the mean and variance, I can estimate some kinds of probabilities. So we'll see some of the examples of this in these coming sections. First section, I'll do this union bound, and I'm just going to follow his discussion in this case and maybe draw a few pictures because it's a quite well organized discussion. Right. Now, so first we have the union bound. So let's go ahead and draw a picture of what's going on here. So let's add a page here. And if we have the union bound, for instance, if we have two events here, so I have my sample space, okay, and then I have two events A and B. Okay, now the probability of A would correspond to the area of A, and the probability of B would correspond to the area of B in this schematic. Okay, so P of A equals area of A, and P of B equals area of B. Okay, now certainly the probability of A union B is going to be less than or equal to probability of A plus the probability of B, right? Because you have this overlap. Right? Now, in fact, what you have exactly is the probability of A union B is equal to P of A plus P of B minus P of A intersect B. Right? Now, this is with two sets. If I do with three sets, you can see something like this. I can do A, B, and C, and you'll see that we're trying to get a general trend of what's going on here. If I have A, B, and C, so A is this circle, B is this circle, C is this circle, okay? So I'm going to have the probability of A union B union C, all right? Now, here I have the probability of A plus probability of B plus probability of C, all right? Now, certainly that's not equal. That's going to be less than or equal to, right? It's going to be less than or equal to this. It's only going to be equal if there's no intersection between them. Now, what I can try to do is to improve that bound by subtracting out the double counted area, okay? So if I take the probability of A union B union C, all right, that's the area here. I could take the probability of A plus probability of B plus probability of C. Now notice here, to get the exact value, I had to subtract out the intersection. Okay, now here I actually have three intersections. I have this one here, I have this one here, and I have this one here. Three intersections. Okay, so I can subtract P of A intersect B. And here let's just put this as a sum, plus P of A intersect C plus P of B intersect C. Now, if I subtract this, I'm subtracting this overlap once, this overlap once, this overlap once. I've actually subtracted this one multiple times. Okay, so I've subtracted it too much. So in fact, this is going to be greater than or equal to this. And it's only equal if there's no three-way overlap. Okay, so this one subtracts the three-way overlap too much. Right? When I did A plus B plus C, so this counts the three-way intersection. It counts it 3 times. Okay, so So P of A plus P of B plus B of C, that counts the three-way overlap 3 times. Let me call this three-way overlap, let me just call this E. E is probably not a good letter because you use that for expected value. Let me call that, I'll call it G or something like that, okay? So P of A has G once. P of B has G once because G is included in B. P of C has G once, okay? And then all of these also have G. So that's, and then we also have included in all the intersections. Okay. All right, so what I've done is I've added it 3 times and I've subtracted it 3 times. So that means that G is not included in the sum. So in this case, with 3 sets, I would get P of A union B union C is equal to P of A plus P of B plus P of C. Then I'd subtract the two-way intersections, subtract the two-way intersections. Okay, I subtract those. Then I would have to add the probability of A intersect B intersect C. Now that works for 3, but suppose I have 4. You can see this kind of alternating pattern here. First I have the sum, then I subtract the two-way intersections, then I add the three-way intersections, and if you go on to 4, 5, 6, 7, 8 sets, you're going to find this alternating pattern. And see, if I stop without considering all of the intersections, I'm either going to overcount or undercount. In this case, with 3 sets, I overcounted. I'm sorry, I undercounted because I didn't count the 3-way. Then here, if I add this back in, then I count it correctly. But if I had 4 sets, then I would be overcounting. Okay? So you alternately overcount and undercount. So I suggest you get more intuition. You can draw more pictures and see how this works out. All right. So the first estimate is you simply take the sum of probabilities of all the sets. So I did it for 3. I did it for 2 also, but you can see this is the generalization. If I take the union of any number of sets, then that's less than or equal to the sum of the probabilities of all those sets. Okay. So we have some example here, which is very nice. He talks about the case of random graphs. And you can generate random graphs in different ways, and they're used for different models. Sometimes they're actually used to model disease. Or here he says in social networking. Okay, so each node might represent a person, and the idea is that you have n nodes, which represent n people, and any 2 people are connected with probability p. Right? So if you think about constructing this kind of random graph, you would lay down the nodes, and then you would randomly, for every possible pair, you would flip a coin, a Bernoulli coin with success probability p, and if the Bernoulli coin comes up heads with probability p, then you would draw an edge between those 2 nodes. Okay, so there's probability p of an edge between any 2 nodes. Okay. So here's one example where p is chosen to be 1/2. Of course, if p is smaller, then you're going to have a graph with fewer edges. And once p gets close to 1, well, when p is equal to 1, you have all the edges drawn, and that's called a complete graph. All right. So the question is, what's the probability that there exists an isolated node that's not connected to anything? Okay. So that's the idea. So you can find a bound for this probability using the idea that we just had. Okay. So let Bn be the event that a graph randomly generated according to GNP has at least one isolated node. Show that the probability of Bn is less than or equal to n times 1 minus p to the n minus 1. Okay. And then he takes the limit of this as n goes to infinity and finds that that's 0. Okay. So how is he getting this? Well, think about how we can divide up the event that there's an isolated node. So there's at least one isolated node. So what's the probability that this one has no connections to any other node? Well, the probability that these are not connected is 1 minus p. The probability these are not connected is 1 minus p. Probability these are not connected is 1 minus p. Probability these are not connected is 1 minus p. So that would be 1 minus p to the fourth power. Because you multiply them together, the different probabilities of connections are independent. Okay? So the probability that this node has no connections to any other node is 1 minus p to the fourth power. In general, if you have n nodes, the probability of no connection will be 1 minus p to the n minus 1 power. Okay? So that's the probability that this node is not connected. Okay? So we actually have 1, 2, 3, 4, 5 events that can be possible. Either this one's not connected, or 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 this one's not connected. So those are 5 possibilities. I can choose those as my 5 sets, or my 5 events. Okay? So the probability that none of them are connected is less than or equal to the sum of the probabilities that each one is not connected. Now that argument is generalized down here. So if you understand the argument for 5 nodes, you can understand the basic outline of this argument. Right? Whoops, so let's open this. Okay. He's simply generalizing the argument that I just gave. Right? So here he says AI is the event, the ith node is isolated. Right? So there's going to be n events because there are n nodes. The probability that at least one is isolated will be the union of those events. Right? At least one means this or that or that or that, and that means the union of those. So here's your sum bound, and because there are n nodes and they all have the same probability, we can reduce this sum to n times, and then here he calculates the probability that one particular node is isolated. Okay. Then he uses this limit of e to the c, which is a common limit, important limit, and then takes the limit as n goes to infinity, does some algebra, and finds out that the limit is 0. Okay. And that's the limit as n goes to infinity. So no matter what p is, you're going to get 0 probability. And that makes sense because if you have lots and lots of possible edges, then chances are that at least one edge is going to be connected to some person. So most likely you're not going to have any isolated people. They'll be connected to someone in the network. Okay. Right. So it's an interesting exercise to calculate PBN exactly using inclusion-exclusion principle. Right. So if you wanted to find the probability exactly, you would have to calculate all of these terms. And what he's saying here is that if you want to get a better bound than the sum bound, you just take more and more terms of this, and you will either overestimate or underestimate. And I showed how that worked in the simple case with just 2 sets and 3 sets. With 2 sets, you're going to overestimate the probability because you're going to be subtracting the pairwise intersection too many times. But if I have 3 sets, I'm going to be underestimating the probability of the union because I subtract the intersection of all 3 too many times. Right? So you can see that here. So you have this sequence of probabilities. Now you can see here that what he's done is he's simply all right, so if you look at this example, let Bn be the event that a graph randomly generated according to GNP model has at least one isolated node, show that the probability is greater than or equal to this term, which we saw before, and then minus this term. Okay. So this is going to be using the second Bonferri inequality. This term we've seen before. This term, 1 minus p to the 2n minus 3, well, that's the probability that any 2 given nodes are isolated. Right? You can also work that out in the case of 5 connections. If two nodes are isolated, that means that these 4 connections are not connected. And then here, these 3 additional connections are not connected. So that would be, for these two, that would be 4 plus 3. So this is going to be n minus 1, and then this is going to be plus n minus 2. So if you add those together, you're going to get 2n minus 3. So you have to have 2n minus 3 missing connections in order to have 2 points isolated. So that's where the 2n minus 3 here comes from. Where's the 2n minus 3? That's where the 2n minus 3 here comes from. And there's actually choose 2 possible pairs. Right? So you can read that argument here. It's expressed very clearly. Now this is quite an important point down here. He says that the union bound is actually equal to the expected number of occurred events. Expected number of occurred events. And you can kind of see that because when you add, it's just like adding expectations, right? We know that if we have the sum of random variables, the expectation of the sum of random variables is equal to the sum of the expectations. So what we need to do is express this probability as a random variable. And there's a common trick which is quite useful that enables you to do this. If I have these n different events, I can define a random variable for each one of these events. It's called an indicator random variable. If A1 occurs, then I say x1 is equal to 1. If A1 does not occur, I say x1 is equal to 0. Right? So we have x1 is on or off depending on whether or not A1 occurs. So from the point of view of this picture that we've been drawing, if A1 occurs, right? Here's my A1 here. Now, the probability that x1 equals 1 is simply the probability of A1. So x1 equals 1 inside of A1. Sorry, this is A1. The probability that x1 is equal to 1 is in there. It's equal to the probability of A1. Okay? So what's the expected value of x1? Well, it's going to be equal to, sorry, it's not plus, it's equal to. Expected value of x1 is equal to, well, x1 can take 2 values. It can take the value 1 or it can take the value 0. So expected value of x1 is going to be equal to probability of x1 equal to 1 times 1 plus the probability x1 equal to 0 times 0. Okay? So, of course, this term goes away, so the expected value of x1 is equal to the probability that x1 equal 1, and that's simply equal to the probability of A1. All right, very nice way of relating expected values to probabilities, and we'll see that trick again. So we can define the sum of probabilities of A1 through AN as a sum of expected values. Right? And that tells me that the expected number of isolated nodes is given by this expression in the graph example that we saw above. All right? So hopefully talking through that description, you can understand better what he's talking about in this section. Okay, very good.